This is Lecture 12 in BBSP 610. Today we're going to discuss how you calculate confidence intervals for the mean. So in the previous lecture, we were given the true population mean and standard deviation. We computed probabilities involving the sample mean x bar. And that's useful for illustration purposes, but it's completely unrealistic in practice because you won't know the true values of mu and sigma, the true population parameters. What's more useful in practice is you use the sample mean x bar and the sample standard deviation s to tell us something about mu and sigma. So inference, when we talk about statistical inference, it means that you use sample data to draw conclusions about a population. In the previous lecture, given mu, we obtained information about x bar, not useful in practice. What we will normally do in practice is we're given x bar, we take a sample from a population and want to use that to draw inferences about the true mean mu. And recall from the previous lecture that for large values of n, the sample mean x bar is approximately normal with mean mu and standard deviation sigma over the square root of n, and hence x bar minus mu divided by sigma over square root of n is approximately normal with mean 0 and standard deviation 1. So if we want to find a 95% confidence, I'll show here how we can use these facts to find a 95% confidence interval for mu. So the first step in doing this is to find the appropriate quantiles of a normal 0-1 distribution. This graph shows the density of a normal 0-1 distribution. As we've discussed before, you want to find a lower quantile and upper quantile such that 95% of the data is between the upper and lower quantile. You can use that in R using the qnorm command as we've discussed previously. As it turns out, for a standard normal distribution with mean 0 and standard deviation 1, the 97.5% quantile is almost exactly 1.96. Consequently, the 2.5% quantile is minus 1.96. So based on the equation in the previous slide, we know that the probability that x bar minus mu over sigma over square root of n is between minus 1.96 and 1.96 is 0.95. So if we rearrange that equation using algebra, we ultimately end up with the probability that x bar minus 1.96 sigma over the square root of n, or rather the probability that mu is between x bar plus or minus 1.96 times sigma over the square root of n is about 0.95. In other words, we can make inferences about mu using x bar. Given x bar, we can come up with an interval that's chosen such that there's a 95% probability that it contains mu. So how do you calculate these confidence intervals in practice? If you look at the formula on the previous slide, we can get a 95% confidence interval by taking x bar plus or minus 1.96 sigma over the square root of n. This won't work in practice because you won't know the standard deviation sigma. So instead what we do is we take x bar plus or minus the appropriate quantile of a t-distribution times s over the square root of n. And the t-distribution, I won't go into it in tons of detail, but it's a distribution that's similar to the normal distribution, but it has thicker tails. This slide here illustrates how it works to a certain degree, that a t-distribution with 1 degree of freedom is bell-shaped but has thicker tails. As the degrees of freedom increases, the tails get narrower. As the degrees of freedom goes to infinity, it approaches a standard normal distribution. And this takes into account the fact that if we don't know the true value of sigma, then the confidence interval needs to be a little bit wider to take into account the fact that we're estimating sigma as well as mu. So rather than using the quantiles of the normal distribution, we use quantiles of the t-distribution, which makes the confidence intervals a little bit wider. For sufficiently large n, the t-distribution is almost identical to the normal distribution anyway. Here is just a little comment about how to interpret confidence intervals, that sometimes people say that there's a 95% confidence interval, that a 95% probability that the confidence interval contains the true value of the mean. That's technically not a correct statement because the mean's is a fixed value even though we don't know what it is. So it's either contained in the interval or it isn't. So it's probability 100% or 0%. Well, the correct way to say it is that there's 95% probability that we choose the confidence interval such that it contains the true value of the mean, or we're 95% confident that the confidence interval contains the true value of the mean. I'm not going to be super picky about that in this class, but I thought that was worth noting because some people will get really angry with you if you say it wrong. So this slide illustrates a bunch of simulated confidence intervals. That this was data generated using the random number generator in R. It was generated to have mean 50 and standard deviation 10, and they selected 10 observations from this distribution, averaged them, and calculated the confidence intervals. And the true confidence intervals should contain 50 because that's the true mean, and you can see here that most of them do. There's only 2 intervals that don't contain the true value of the mean, and if you look here you can see they just barely miss as well. So generally speaking, these confidence intervals will cover the true value of the mean or won't miss it by very much. And if you increase the sample size, it'll make your confidence intervals narrower, which makes intuitive sense. If you have a large number of observations, the standard deviation gets smaller, you can estimate the mean more accurately. However, even though they get smaller, this doesn't increase the chance that the confidence intervals contain the true value of the mean. In fact, if you look here, with this larger sample size, the sample size 25, by the way, even with this larger sample size, this time there's 4 intervals that don't cover the mean rather than 2, so that in general increasing the sample size will make the intervals narrower, but it does not increase the probability that the interval will be selected such that it contains the true mean. If you want to be more certain that you're going to cover the true mean, what you can do is increase the confidence level. This will make the confidence intervals wider, but it also increases the probability that you're covering the true mean. Here, it's the same data from the previous slide, but we calculate 99% confidence intervals rather than 95% confidence intervals. In this case, there's only 1 interval that doesn't contain the true mean, and it just barely misses as well. So here's some examples of how to calculate confidence intervals in R. This is data given to me by a former student in this class where she measured the urea secreted by 27 liver cell samples. I posted this data set on Sakai if you want to try any of these examples yourself. So in this case, the upper and lower 95% confidence bounds are x bar minus appropriate quantile of the t-distribution times s divided by the square root of 7. The upper confidence bound, you just replace the minus with a plus. So how would we do that in R? I read in the data, and then I take the mean of the data. To calculate the appropriate quantile of the t-distribution, the command in R is called QT. I want the 97.5% quantile with 26 degrees of freedom, times the sample standard deviation of the Urea data divided by the square root of the sample size. So, in general, the command in R, Qt of P, df, will give you the pth quantile of a t-distribution with df degrees of freedom, so Qt 0.975, 26 is the 97.5% quantile of a t-distribution with 26 degrees of freedom. There's another way to do this that requires less typing. It's the t.test command in R. If I just say t.test of Urea, see it gives me 95% confidence intervals that are identical to what I got when I used the formula directly. So in general in R, the t.test command's really versatile. There's tons of different options. I'm not going to list them all right now. We'll use it quite a bit over the course of the next few lectures. For the time being, if you use t.test without typing anything else, it'll give you a 95% confidence interval for the mean of x. Let's say we wanted a 99% confidence interval. You can tell R to give you a 99% confidence interval by adding the parameter conf.level to t.test. A t.test Urea conf.level equals 99. That gives us a 99% confidence interval. We see that's only slightly wider than the 95% confidence interval. So why would you ever want to do the mean plus QT times SD thing that I did earlier when we can just use t.test? The answer is most of the time there isn't much reason to do that, if I'm being honest. The t.test is what I use in practice the vast majority of the time because it's quicker and easier and you're less likely to make mistakes. The only reason you might want to use the other version is the t.test requires you to have the original data so that R can calculate this stuff. If all you have is the sample mean and the sample standard deviation of the data, if you don't have the raw data points, then you can't use t.test. You have to calculate it manually using the procedure that I described earlier. In practice, that doesn't happen often, but if it ever does, that's how you would do it. Oh, just to illustrate things that can go wrong if you apply confidence intervals mindlessly. It's easy to calculate confidence intervals in R, but they're also easy to mess up and abuse. That a lot of times people just want to input their data into R and immediately run out and publish their numbers without checking to make sure that what they're doing is reasonable. And honestly, for the purposes of this class, I'm much more concerned with whether you use confidence intervals correctly than whether you know how to calculate them. If you forget how to calculate confidence intervals, you can look at your old notes, you can look in an old textbook, you can ask a lab mate, email an old professor, whatever. But if you remember how to calculate a confidence interval but calculate it incorrectly and report spurious findings in your paper, there's nothing that can be done about that. So I'm going to illustrate a couple of things that can go wrong when you calculate confidence intervals. This was an example of in a textbook that I used when I put this class together, that there was apparently a study one time. They found people who used marijuana heavily for religious reasons had an IQ of about 128.4. The average for the population is about 100. I believe the standard deviation is about 15. This is an impressively high average IQ. Can we use these numbers to create a confidence interval for the average IQ of marijuana users? Maybe contrary to popular opinion, marijuana actually makes you smart. Well, The big problem here is this isn't a random sample from the population of marijuana users. The formula for the confidence interval only considers sampling error. It doesn't take a biased sample into account. If your sample is biased or otherwise not representative of the population, you are dead in the water coming straight out of the gate. It does not matter how large your sample size is. If you remember back to the first lecture, the Literary Digest poll in 1936 that predicted that Alf Landon would beat FDR in a landslide. To this day, that is one of the largest surveys ever conducted in the United States. It had something like 1 million respondents, as I recall. But even a sample size of 1 million, if your sample is biased, you will get incorrect results, and your confidence intervals will be completely meaningless. Another place that you can get it go wrong is that in order to obtain valid confidence intervals, your observations have to be independent. An example where this might be violated is a study that I worked on a few years ago where we had 84 patients in our clinic. We measured their blood pressure twice and we want to find a 95% confidence interval for the blood pressure. How would you go about doing this? First of all, hopefully you're paying attention. You're wondering whether a sample of patients in the clinic is representative of the population of the whole. Is it even necessarily representative of the population who has the condition that you're studying? People who come into the clinic for health care are more likely to have insurance, for starters. They're also more likely to be educated, more likely to be wealthy, more likely to be female. So all these things could bias your study straight out the gate. But aside from those concerns, you need to choose the degrees of freedom carefully here. If you read in this blood pressure data, it's a data frame with two columns, one for their first measurement and one for their second measurement. This data set should be on Sakai if you want to experiment with this. If I just mindlessly concatenate the two data sets together and apply t.test, I'll get a confidence interval, but this confidence interval is wrong, as we'll see here in a minute. That when we measure it twice for every subject, these two blood pressure measurements are not independent. In fact, they're very strongly dependent, so if we mindlessly use all of the observations, we end up with a sample size much larger than what the true effective sample size would be. In this case, the simplest way to get around this issue is to average the two measures for each patient and then find a 95% confidence interval for this average. So the code to do this in R is take the first measurement plus the second measurement divided by 2 and then do t.test on that average. If you compare this to the confidence intervals from a couple slides back, they're a bit wider. So if we don't average the two measurements for each patient, then the confidence interval is too narrow, and in general, if you have non-independent data, you can, or let me rephrase that. In general, if you have repeated observations on the same subject and you want to find a confidence interval for the mean, then a simple way to deal with that problem is just to average the repeated observations for each subject and then take the average of the averages. I mean, that works, but it can cause problems if, for example, you have 60 mice that come from one of 10 litters. If you average across the litters, you end up throwing away a lot of data. There's more advanced ways to do this that we won't be covering in this class. I'm happy to talk to you if you ever have encountered data like that in your lab work or whatever. And if there's dependence throughout your data, say that you have time-ordered data that I worked with a student on this where he was like measuring the position of moths' wings over time, and obviously the position of the wing at time t is very strongly correlated with the position at time t plus 1. In that case, you're better off consulting an expert. There's advanced methods that are beyond the scope of this class. Another way that you can, in theory, get into trouble is that the t-distribution also assumes the underlying population is normally distributed, but in practice that's usually not much of an issue because the central limit theorem will save us even if the underlying data isn't normal. Usually if you have 20 to 30 observations, you're fine. If you have 70 to 80 observations for really bad data, you should still be fine. But if you're working on a really small sample, then you can get into problems if the data is not normally distributed. So I often get the question, how do you know if a data set's normally distributed? As I said, in practice you very rarely need to worry about this because as long as you have a reasonably large sample it doesn't matter, but occasionally this is useful for other areas of statistics, and there was some extra time in this lecture, so I decided to briefly describe how you would do this. There's statistical tests for normality, but in general they don't work very well. The easiest approach, even if it's a little less rigorous, is to just draw pictures, specifically what's called a normal quantile plot, which means that we plot the quantiles of our data against the quantiles of a normal distribution. If the data is truly normally distributed, this should be a straight line. And once upon a time that was painful to do, but now it's easy to do using R. The commands that you need are QQ_norm and QQ_line. I did this on the Michelson-Morley data from a few lectures back, and I'll show you the plots here in a minute. But just so you know what these commands mean, if you say QQ_norm of X, that'll plot the normal QQ plot for a data set X, and QQ_line will draw the line. We'll draw a line that the data would follow if it were perfectly normal. You don't really have to add the QQ line, but I normally do because it makes the graph easier to read. I suggest you do the same. So here's the QQ normal plot of the Michelson-Morley data. It isn't quite on the straight line. You see it starts to get a little above or below the line as you go out to the tails, but generally speaking it's not too bad. So you could probably safely say this data is, if it's not exactly normal, it's close enough. It's close enough. And here's a histogram of the Michelson-Morley data. And we see it's approximately bell-shaped, so probably pretty close to normally distributed, other than the fact the tails are a little larger than we would expect. Here's a histogram of the Loblolly Pines data. As you'll recall, it's multimodal, it has several peaks, not anywhere close to being bell-shaped, so we would expect this not to be normally distributed. If you draw the normal QQ plot of Loblolly Pine data, you see indeed it's not anywhere close to being a straight line, so we conclude this data set is not normally distributed. Here's another data set from R on rock permeability, and you can see it has a very heavy right tail. Most of the observations in the data set have low permeability, but there's a heavy right tail with higher permeability. We draw the normal QQ plot there, and once again, it's not anywhere close to being a straight line. You would conclude that this data is not normally distributed. So the things to remember for today's lecture is you can compute confidence intervals for the mean using the t-distribution. For confidence intervals to be valid, the data has to be a random sample from the population of interest. The observations also have to be independent. If you have a small sample, it needs to be normally distributed. In practice, that's less likely to be an issue. You're more likely to get into trouble with confidence intervals if you have a non-representative sample or if the observations aren't independent. But if you ever do need to test normality formally, you can use QQ plots. Here's the R commands that you can use to do this type of analysis. QT will give you quantiles, the t-distribution. T.test you can use to calculate confidence intervals. QQ norm and QQ line can be used to produce normal QQ plots to test if your data is normally distributed.